Welcome again to the Red Dirt Agronomy Podcast. My name is Dave Deacon. This is episode 106, so thank you for making your way back again. Now, we do have a quick favor to ask of you. Please jump over and hit the subscribe button on your streaming service so you will be one of the first people to know when the new Red Dirt Agronomy Podcast drops every other week. As usual, we're coming to you from Dr. Jason Warren's research lab on the agronomy farm at Oklahoma State University. And you've joined us on another great episode. And this time we'll be talking with Dr. Andrea Yelling, whose primary focus at Oklahoma State University deals with soil organic matter dynamics and soil-plant microbe interactions. So there's a pretty strong chance that you'll be walking away a little bit smarter. Now, with this being a podcast, we're not able to put lower thirds on the screen, so we'll make a quick trip around the table so you will know who to tweet when you don't agree with what they're saying. We'll start with Oklahoma State University Extension Cropping System Specialist.
I'm ready to go to anhydrous. I thought we were going to anhydrous. No, I have no questions about anhydrous. You just sounded really excited about anhydrous.
Dr. Josh Lofton. And to his right is a guy who's devoted his life to rummaging through soil.
Well, I know. I mean, that was what I was going to say. Is like, I'm going to eat the sugar and I'm going to love it. And then I'm going to get all hopped up.
Those are the golden tones of Oklahoma State University Extension Soil and Water Conservation Management Specialist, Dr. Jason Warren. And across from Jason is a guy who's known as much for his fashion when he wears America's Brightest Orange lab coat as for his work in the world of soil fertility.
You were almost serious enough to get me to believe you, but it had been way too many years. I'm like, the Michigan was a new add-on.
That, my friend, is Oklahoma State University's Extension Precision Nutrient Management Specialist, Dr. Brian Arnell. If you would like to ask the group a question, then jump over to reddirtagronomy.com and leave your question there, or send us an email directly, podcast@reddirtagronomy.com, and we'll discuss your question on the next podcast. And that's where we start this episode, with a question submitted from the website. Thank you, Lucas from Major County, Oklahoma, for writing. And now here's Dr. Brian Arnell with Lucas's question, and you are listening to the Red Dirt Agronomy Podcast.
So the question is, if we're looking at effectively a failed wheat crop in northwest Oklahoma and a fair amount of western Oklahoma, and going to try to follow up with the double crop sorghum, how do we account for that nitrogen and how much credit do you give to that sorghum crop, and how do you manage that sorghum crop fertility? And so we look at it this way, and so there's a couple aspects you got to consider to take in your total account. And when was the nitrogen applied? How was it applied? You can credit yourself with some efficiencies on that point. Did you get the nitrogen on the ground and have it actually rained in? There's a lot of top dress nitrogen that never got rained in, so we have to question how much of that's actually in the soil. If we were able to get the nitrogen into the soil system, since we don't have the loss of crop is due to drought, so therefore we aren't going to be leaching, so we don't have that downward movement. We could, in theory, have upward movement, meaning ammonia volatilization that's going to occur on the surface of a high pH soil, but that's in conditions where we have a soil pH greater than about 7.4. We have the conditions of dry and wind, but in most of the cases where this question is taking place, we're going to have soil pHs sub 7. So ammonium volatilization is going to be a little bit lower. So our loss pathways are a lot less. So we're really not worried about leaching. Ammonia volatilization is minimum. So the nitrogen would be there for the sorghum. And you could account a great amount of that, whatever made it into the ground, for that sorghum crop and be available for the sorghum crop. Now here's a caveat. No-till. This is where that value gets to be a little bit more challenging, and also the existing wheat crop. So if we're in no-till and we're looking at a liquid application using UAN, whether it's streamer or flat fan, if that liquid hit the crop residue and didn't get rained in very quickly, there's a great opportunity for it to be tied up in that residue that's on the soil surface. So the dead and decaying material, it has not decayed. We're in a drought, it hasn't rained, decaying takes moisture, so we're not breaking it down. And so you have to say that, okay, you haven't lost that nitrogen, but that residue has to be broken down, and that nitrogen then has to get into the soil system before the plants have capability of it, or access to it. So you've got to start taking away aspects of that nitrogen applied to the wheat crop depending on how you applied it. So liquid in no-till how much residue's there. If there's very little residue and you had liquid on the soil surface, and you're probably pretty good. I would account 75% on a conservative level. If you have a lot of residue, now you start to have to take it back. So if I'm really, really heavy residue, most of my liquid hit that crop residue or that old residue, now I might have to cut it back to 50 or even 33% immediately available. If it all works out well and it starts raining in the spring and we keep rains, that residue is going to break down quickly. It's not going to be available in the first 30 days, but would be available during booting and grain fill in that summer crop if we have rain, which will probably, Josh, not going to make much of a crop on a double crop if we don't have rain anyways. If you're looking at urea, kind of have a mixed bag there. With a dry application of urea, if you had gone out during the drought and spread it even in no-till, the way that urea prill is in a dry and low humidity atmosphere, it's going to work itself through the residue and near that soil surface. So the moisture is going to get it, and you'll have some tie-up, but not near the same level of tie-up as liquid nitrogen going on the top. So it all depends on the scenario, how it was applied. Was it pre-plant incorporated, in-season, no-till, how much tillage, and even so, that nitrogen, if it's in the soil now, there is going to be forces at work in the soil, which we'll get in with Andrea later about, what are those forces that are going to be acting upon the available nitrogen to break down the organic matter that has not broken down over winter and the spring, which we would normally expect to. So we're going to have some microbial and plant battles, and microbes usually win.
How long is that prescription good for? If everything that you talked about relies on moisture. Lack of moisture potential is great. I mean, in the past few years, we've had those heavy May rains, but we may not get those this year. What if we stay on the track that we're heading on as far as moisture goes? How will that play a role into it?
It's not going to go anywhere, but neither is your sorghum crop. So that goes back, I think Jason said it before we started the podcast, is how much are you going to fertilize a double crop for sorghum after failed wheat crop? I'm not putting a whole lot of money in that bank, especially pre-plant. The current cost, we're looking at prices potentially. There is indication nitrogen might go down a little bit. It might be a faulty indication, but prices have dropped in the last week or so. And so we're looking at, do I want to spend expensive nitrogen still on a crop that we have zero water in the bank, the soil bank? No, I'm going to live off of a borrowed dime and go with what was in the wheat crop and kind of go from there.
So, Josh, on top of that, how is the potential for sorghum this year across, western, north central Oklahoma? He's looking at his crystal ball right now. He's finding the answer.
Does it depend, Josh?
Yeah, it depends. I mean, if you look at what our potential forecasts are for hot and dry through July, I don't think it looks good. That's not to say everywhere will be, but of course we always get the pockets of rain and stuff like that. And some fields it'll be good, and some fields will be bad. But with the current forecast and, we see rain chances out 7 days, especially west of 35, we see those rain chances out 7 days. And by the time it's two days ahead of time, it's basically zero. And anything we're getting is, sub half inch. So, I would say for the bulk majority, it doesn't look good for an outlook. And that's one thing that we've always said about double crop is don't risk it. It's a stressful situation. It's a high stress system. Don't risk it if it's already has a stress to it, and in this case, moisture stress. But I want to go back to what Brian said. So that was after failed wheat crop. What about a subpar? So like
subcrop failed.
You didn't fail. You fertilized for 60, but you're going to get 20.
Celebrate the 20 from what I've seen in the field would be.
But for the fertility,
I'm with you.
For the fertility
so if we look at that,
is it still that same 1.3, or do you have to take some off the top? Like where do you draw that connection between what we typically think of nitrogen per bushel by what the crop took up to potentially get 65, but is never going to get 65?
Quickest math you could do, the easiest math is just for each bushel you take off 2 pounds. Say, okay, I pulled 20, so I'm going to subtract 40 off the top. Now, depending on what you get in your crop scenario, you can easily skinny that down and say, I'm going to pull 1.5 pounds off. But most people are going to be conservative in the other side that, okay, I've removed more than I'm going to expect. So two's a happy number in this environment. As dry as we've been, we've had, if the wheat survived, it rooted as well as it could root. We've probably scavenged as well as we could scavenge this year. And so the wheat we've had has probably been somewhat efficient as far as nitrogen goes. That's going to make it. But 2 pounds of N per bushel, if you take 15 bushel off, give yourself a 30 pound minus of whatever you apply to that wheat crop. But again, I'm trying to remember back in the fall at planting time, we didn't had good moisture, but we never really had heavy leaching rains.
No, I didn't have freaking leaching rains since a year ago, if not 2 years ago in most of Oklahoma. The one thing, just thinking, like if you had conditions for good crop nitrogen uptake, and then you're getting your yield clipped, you're gonna have high protein wheat, maybe shriveled.
It's going to be shriveled.
Low test weight.
Yeah.
But then, you had all that nitrogen in that plant, and does that 2 pounds per harvested bushel, does that account for like your ammonia loss from the plant during anthesis and the breaking? You know what I mean?
No. Yeah, no, that's a huge aspect of wheat, which is a poorly inefficient crop. So, Josh, this will go back a little bit of what you said. So, in a timing. So, let's give it maybe on some of this grazed out wheat. Or not grazed out, the dual-purpose wheat. Earlier planted wheat probably had a higher dose of nitrogen to it, had a lot more early-season growth. This wheat that went blue first, wheat is a luxury consumer of nitrogen. It's going to take out as much nitrogen as it can, put it into that leaf tissue, taking up nitrate, taking up ammonium, converting it to ammonium to then go to the amino acids. Well, in luxury consumption, you're storing ammonium in the leaf tissue before it converts to amino acid. That ammonium in stress times, specifically around anthesis, flag leaf through anthesis, if you have drought stress, now that ammonium accumulates, starts becoming a little bit toxic, and now you have to kick it off as ammonia gas. So Bill Ron, back on the long terms, I want to say mid to late 90s, showed that in Oklahoma, we could gas off anywhere between 30 and 50 pounds of nitrogen.
Boom.
But I would say in that year, they had a lot better growth. So we're talking big wheat.
Yeah.
And then drought stress.
The
one aspect of this year is we had drought stress so early.
Yeah.
We got kind of big wheat. And so we, without question, have probably gassed off some on that early applied nitrogen. In-season stuff I'm seeing right now, we had good uptake. If you put it on in January and February to places that had an incorporating rainfall, there's been uptake, but I'm not 100% sure we've gassed off. The 2 pounds of N, that is more of a soils loss because it's 1.67 pounds of N per bushel of wheat, somewhere around that, 1.43, 1.67 pounds of N in a bushel of wheat.
Yeah.
And that 2 is soil losses and some plant loss. In a year where we had a better fall growth and got bigger ranker growth and then went drought stress, you'd easily have lost a pound of bushel.
Well, and that kind of goes to my last point or question is, when you have a crop fail like that and it doesn't ever get to physiological maturity before, say, you get the insurance guy out there to zero it out and then you can burn it down and plant. And Andrea may be able to comment on this too, but those plants that did not fully mature, they're not going to be as resilient to decomposition. But you're saying that they could have lost a lot of nitrogen from them as they were dying, right?
Yeah, the plants that are out there are going to decompose a lot quicker than any of that residue.
The
here's my question.
residue.
Post-harvest.
Yeah.
How many people that are insurancing out aren't going to swap that for hay, since hay is going to be so valuable this year, have already turned out cattle? I know up in Alva they've released cattle all over the place. So, how much of that biomass is going to be left on the field? So, which goes back to, you might have zeroed out your grain, but if we swathed it, then you got to start talking about 40, 50 pounds per ton of forage harvested.
Yeah, good point.
The nitrogen that's lost from the tissues, like you were saying, I actually wasn't aware of that pathway, for one. And, how much nitrogen are we talking sometimes?
In the excess, I think in Bill's work, which was just right out here on the agronomy farm and at Lahoma, because that Lahoma environment could really stress, they were documented up to 75 kilos per hectare. So that's about 70 pounds of N per acre that was of all the pathways measured in Oklahoma winter wheat, the late season plant loss was the greatest of all factors.
Yeah, and he did it with a mass balance type deal. He tried to keep account of all the nitrogen, and then there was that much missing. And the only rational conclusion, and he and I actually bounced back and forth the idea of somehow like directly measuring it, but on small plots it's kind of hard to do. From just the soil surface you could do it, but if you're trying to collect that gas quantitatively from the plant on a small plot basis, it's kind of hard to do. But it's kind of cool.
That just makes me think about that stat where, like, out of all the fertilizer we apply, or end fertilizer, only up to half actually makes it into the plant. But could that actually be? No, actually, a large portion makes it into the plant. It's just lost.
Yeah.
So that half or 33% isn't even just plant that's in the grain, right? And so you have all that plant material that goes back in that's cycled, and so it's definitely can be lost in there. And it's a seasonal, just like leaching. It's a very seasonal. If we don't have leaching, we might have more plant loss.
Yeah.
Now, I do want to take a quick second here to introduce our guest, Dr.
Fantastic.
Andrea Yelling here at Oklahoma State University. So Brian, tell us about your guest that you brought today.
Dr. Yelling is our soil chemist, brought in. Andre, you've been here about a year and a half, 2 years?
2.5 years.
2.5 years now.
I know, most of it COVID times.
Yeah, I know. That's right. We barely know her. But she's been great to work with. So we wanted to bring her on because her specialty is, and I want to really let her talk about, is more of that organic chemistry and getting to work with her on some of the stuff I'm doing on wheat and sorghum as far as that organic chemistry, the microbial relationship with what's going on in the soil. And so kind of really good timing to bring her in on this conversation.
Yeah, so you said it right. Really thinking about really the organic matter in soil, that's what we're focused on. And specifically the carbon and nitrogen in organic matter with, thinking about not only how soil organic matter can store carbon and nitrogen, but also the processes that lead to the release of carbon and nitrogen. We're often thinking about, these two functions of soil organic matter. It obviously has to store a lot of nutrients, but we also are relying on it as a source. And these functions are like seemingly opposing, right? But we need to be able to promote both of these functions in soil. And so our work tries to kind of look in that soil organic matter box and all these many functions, all the many kind of chemical, compounds that exist in organic matter. We think about everything from a leaf that's barely decomposed all the way down to like an individual amino acid. So this wide spectrum, because they all, when a microbe interacts with these different types of organic matter, then they will behave in different ways. They'll be available to that plant or to a microbe in at varying rates, and then the fate of that carbon or nitrogen molecule will vary depending on its initial chemistry. So these are the types of things we're thinking about, which it can be quite kind of fine scale mechanistic stuff happening at the scale of a micrometer or millimeter. But what I really like about being able to do this work here is that we're finding ways to scale it up to plot field scale and understand kind of why it matters agronomically, which is why I love working with these guys, is because they do a lot of this awesome kind of field-based work where we can go in and ask a lot of basic, emerging questions about nitrogen and carbon.
So Andrea just had her first master's student just defended a couple weeks ago, and so Tanner Judd, and he's going to go out in the real world and get a PhD elsewhere. But can you give like a little synopsis of what his work was, because it was really fun.
Yeah, he was looking in the long-term plots. Where they've been applying different rates of nitrogen for many decades now. And he wanted to look at how organic matter was responding to this, long history of nitrogen fertilization. So not only the total carbon and nitrogen and how that's responding, but the specific forms of organic matter that we were thinking about there's many different ways of kind of characterizing organic matter, but the way we do is we look at particulate organic matter and mineral-associated organic matter. The particulate stuff is like the leafy detrital matter that's barely decomposed, and by definition it's sand-sized. And then we have the more decomposed stuff that is silt and clay-sized. These are the molecules like amino acids that you can't actually see with your naked eye, but is where really the most of the nitrogen is stored, is in this fraction of organic matter. So in the lab we have a way of separating out these different forms of organic matter, and he was looking at how nitrogen fertilization was affecting this particulate and mineral-associated organic matter fractions. And also looking at kind of the biological response to this long-term fertilization. So specifically the biological properties that release nitrogen from organic matter. And yeah, it's interesting. We found these two different types of organic matter, particulate and mineral associated, to be responding in kind of distinctive ways. So there's not kind of one homogeneous response, these different forms are particulate organic matter. If I'm remembering, I have to think back to his thesis. It was only 2 weeks ago, but already those memories, they fade. But particulate organic matter was increasing in nitrogen content, which wasn't surprising, but it actually wasn't as large an increase as you'd expect. This is the fraction that should really reflect the most recent inputs, the litter inputs into soil. But we're finding that the mineral-associated organic matter is also increasing, and sometimes in like a more significant way. And this is the silt and clay mineral-associated stuff is a type of organic matter we really don't, I don't know about you guys, you don't think about as actively in kind of your soil tests and you're thinking about active nitrogen cycling in soils.
I've always kind of figured that was one of the last things we would increase.
Right. It's kind of like relatively passive. It does, depending on the system, can increase slowly, and like the percent increase is not that big. But when you're talking about a pool that's already very large, like that's a significant increase, where any small change has this big effect to like total nitrogen that's in the system. And it's this pool that we think of again as like passive, inert. It's kind of, once nitrogen gets in there, it's kind of stuck there. So we don't think of it as this dynamic pool, but we're seeing it actually does respond to management occurring, well, in this case, on the order of like decades of research or of fertilization and management, but it's still significant, I think, in that it's a pool that we can manage, and we should be thinking about. But the big question now is kind of what's its role when you're thinking about nitrogen management and fertility in general. What we're learning is that this silt and clay associated stuff is actually not as passive or inert. That plants and microbes have ways of accessing this pool that we should be thinking about and accounting for somehow. And it may not be enough to just look at total carbon, total nitrogen. We should be looking at these specific forms of organic matter that are in soil. But that's definitely, his project is going to initiate so many other follow-up projects. There was a lot that, as the first master's student, a lot that you learn from that process. But I think, these long-term plots give you a lot of opportunities to answer these sort of mechanistic questions.
How deep, on that project, how deep did you sample all that? Was that just surface?
Just surface, yeah. Mm-hmm. So we probably went too deep. I think we needed to only go in like the top 5 centimeters or something for some of our biological measures, like nitrogen mineralization.
Yeah.
Yeah, because we found a lot of variability, too much to see a real story for some of the measurements, and we think it's probably swamped out by some of the processes happening at depth. That.
Yeah, if you look at Zhao's stuff, which was every inch, versus Tanner's stuff, which was a 6-inch sample.
Yeah.
If you took Zhao's stuff to full 6 inches, the differences were really, really massive. If you just looked at that top 1 or 2 inches, the difference was really, really drastic.
Yeah, a lot of action in the top 2
when
inches.
When they've ever sampled, and whether this is what you guys did recently or even in the past, when they've ever really sampled these long-term studies and like ran ammonium or nitrate on them, do they see a trend in like elevated mineral nitrogen in those high treatments? Or because years ago I did it and I thought it was a shotgun blast, and I couldn't tell which, just by looking at those organic or inorganic nitrogen, I couldn't tell which one was heavily fertilized and which one wasn't, unless you looked at the plot plan.
On the inorganic nitrogen, ammonium and nitrate, only after years like this do you see anything.
Yeah.
After good years, even the heavily fertilized tends to come back down near
where
near low
nothing's
end.
been able to really happen.
And it could even be bimodal in yours, right? Maybe the check is drawn, and that's some of the stuff, the zero in, and how the zero had some stuff I want Andrea to talk about later. But the check might be here, and it draws down, and you go up, right? So you have the low fertilized, might be the lowest. The check is up there in residual.
It'll have as much residual.
As some of the middle rates in certain years. Well, you think about it, it's that stress, and so I think it's one of these things where you give it a little bit, and it starts really taking off.
Is that called the priming effect?
The priming effect, which was
Ron.
Dr. Westerman.
No,
No,
was
not
that
Ron. That's
Westerman?
Westerman.
That was pre-Bill?
That was Dr. Robert Westerman out in the Panhandle.
And for those of you filling out your vocabulary test today, the word was priming. Yes, be sure and check that off your list.
Why don't you tell a story about priming, Jason?
Well,
I've talked too much already.
Well, it's essentially, I don't know, you do it. I can make fun of you if you
Well,
do
my
it.
definition of priming might actually differ slightly.
Yeah.
You're
Yeah,
talking
yeah.
about nitrogen additions priming.
Yep.
Can you define what that is?
So,
I'll describe mine.
so the theory that was put forward by Dr. Westerman, so this would have been back, I want to put mid-'80s to early '90s, and it came out of actually OPREC, so the Goodwell stations where they documented this, is that I don't know what that means.
Well, 'cause we can't get a nitrogen response on
You're
it.
right on
That's
that
what
one.
I'm saying. You put a little fertilizer on there, you get a little priming.
So what Dr. Westerman saw was that out in the Panhandle, a unfertilized check would yield better than a slightly fertilized plot. And so the theory, and this goes back to, a lot of the times in research we see results and we have to theorize, about the income. So what it took was that you go out there, it's the same soil that it takes 7 years to draw down to get a nitrogen response. In an N-rate study, the checkout yields a 20-pound rate. The theory was that when you put that low rate of nitrogen into that available nitrate ammonium into the soil, it actually kickstarts the process. And so you have this swelling of mineralization. Or immobilization. I'm sorry, you get the swelling of immobilization by microbes.
So you just kickstart the microbes.
You
and they start
kickstart the
consuming all
microbes,
your
and then
nitrogen.
they outcompete the plants, and so you actually have this.
Oh, see, I'm glad I didn't try to define it because that's exactly opposite of what I thought.
Yeah, I mean,
it was.
there is another definition that is somewhat opposite, which is interesting. Not that I'm saying you're wrong, but it's like depending on the context. Because what my understanding, or it's just another kind of version of priming, is that you are priming the microbes, but in a way that it releases nitrogen and facilitates mineralization. But it depends. So, it all depends on like the conditions in that soil, the chemical conditions. If you're going to get more uptake or release by the microbes.
I think it's the same thing, but it's that cropping cycle. When does that release come out? And so in that drier soil, maybe in the Panhandle, maybe that release pattern, it was post crop, like it came too late. Right?
Well, and that's what I'm saying. Yeah, so both of them make sense. But like out there, if you have a soil that, say, you're growing corn and you do fall tillage and then it's dry, and then you've got all that residue, that high seed-in ratio residue that's sitting there all winter and it can't decompose, and then you kick a little fertilizer to it, then it'll just consume all of it. And then it's probably, I wonder if he was doing that on long-term trials, because then it would be even worse in a long-term study, because that check's not going to have near as much nitrogen tied up, or it's not going to have as much carbon that needs to be decomposed before you can start releasing it, right? That's what we're talking.
So I'd have to go look back at the treatments. I just remembered what they saw. Yeah. But it'd still be the same. You still get a greater release later, and this is what we get with the whole question about how much nitrogen is there, is that it will be there, but will it be made available during the crop cycle that it's needed, or is it going to come out during the winter if we have a wet winter and it has no value if you just did double crop sorghum?
Josh, would you concur?
Sure.
He concurs.
Would you concur?
Well,
you can have a voice this week and you're quiet.
Well, I mean, but the interesting thing is we talked about it just with one of my students' thesis about that same kind of thing, that priming effect of like whenever you integrate, and it goes back and forth to this soil health, cover crops, conservation practices, is that when we look at things in a controlled environment, think a lab or a greenhouse or a growth chamber to where we isolate the ecology, and we say, oh, well, when we do this, it shows a benefit on these microbes, and these microbes theoretically would benefit a corn crop because they, cycle nitrogen, they cycle phosphorus, they cycle sulfur, something like that. But then when you put them in an ecosystem, that doesn't happen as quickly or as actively as you think, because there's competition, or is a release, but then there's a higher scale organism that's consuming that release before the crops can get to them. And we just talked about that of typically that reason why we see that 5-year yield drag on things like no-till and things like cover crops, stuff like that, is because inherently the microbial population, when they're growing, they're able to outcompete the crop that's growing, as opposed to whenever they're at a much smaller rate, they're not as competitive to those crops. So.
And so Jason, and I'm going to say on that Westerman stuff, I need to dig. It might have been limited irrigation, right? So if you had more drying cycles, if you had more drying cycles and more periods of low soil moisture, then it's going to drag out that final release that you primed that kicker.
And then there's a whole other definition of priming that's occurring around plant roots that we think about a lot. I'll just make a quick plug for that one because that's probably what we think about more. But I want people to know about it. So, plant roots that are actively growing are always releasing like simple carbon compounds like sugars, organic acids, and these sorts of things. And microbes, when they receive it, it's like a buffet of cookies, and they just go nuts and, grow in numbers. They are more active, all that. And the idea with this type of priming is that it's, they get all this carbon-rich material, and they grow in number and activity, but at a certain point they desperately need nitrogen, and so they have to seek that nitrogen from the soil environment. So they mine, scavenge for nitrogen is the idea, and release nitrogen, presumably excess nitrogen, for the plants right there, in the plant root where they're seeking nitrogen. So there's potentially, a benefit to the plant. But again, it's like, different plant species differ in how they release these compounds, when they release it, what microbes are in the vicinity. Can it, actually lead to, benefit to that plant? But it's something that we're thinking about a lot.
When the plants release these, simple carbohydrates or whatever, and it stimulates the microbial activity, and then those microbes then consume the organic matter, whether it's particulate or like the mineral fraction, and so that can explain what some of the things we see, maybe better than what I've always explained them, on the stratification of organic matter in long-term no-till soils, and so when I started, there was a big the big deal about carbon sequestration, so we went out and took a bunch of soil samples. And we would see accumulated organic matter in the surface, and then we compare that to cultivated soils, and there'd be, kind of an inversion. But then now, 10 years later, we can actually go back and we can see, even, most of those fields were only 5 years no-till, and now they're 15. And we can see even more gross stratification. And I've always kind of thought, well, it's just because the microbes are always decomposing and churning 365 because it never gets cold enough to stop them. But then you're saying in that 4 to 6 inch zone where you are getting fewer and fewer roots, those roots are releasing stimulus that could actually be causing that to decompose. Yeah, because I always figured
there's less
go ahead.
Old root matter to be decomposed, and so you have that drawdown.
Yeah, and then the surface accumulates organic matter only because it's more harsh than the subsoil, right? Because of the drying and heat and temperature, and you know what I mean?
Yeah,
I'm
following. Yeah,
so
it could be the roots that are less disturbed, right? There's just more opportunity for their inputs to accelerate.
Yeah, well, I don't know exactly what I'm talking about. That's why you're here.
I want you to isolate that soundbite right there.
But we have a winner. That's not my new ringtone.
Because at the surface of the soil, we'll see an accumulation of organic matter. And that has to be in part because it's not a pleasant place for a microbe to live, but yet, or else it would consume it really fast. And, that's where you're going to have high levels of variation in temperature and moisture. And then you get down in that 4-inch zone, and the environment's more stable. But if you're stimulating microbial activity with root growth, Because you would, like, roots should be more stable organic matter, right?
Mm-hmm.
Because they're more recalcitrant. I mean, have you ever looked into that kind of stuff?
Yeah, the root and the fate of root carbon versus shoot carbon. Yeah.
Talk a little about that.
Yeah. I mean, I think a lot of people are wondering, are you talking about like in no-till, there's this stratification, like high concentrations at the surface, which you're saying, I never thought of it that way, that it's more extreme. Not that you're wrong, but just that it's more extreme, and that's
it's
what...
okay to say he's wrong.
No, but I always assume
care.
relative to tilled systems, it's just, there's less disturbance. There's less incorporation and physical,
Yeah, when you bury
it's
something, it's in an environment that's more stable.
Right.
Than at the surface where it's wetting and drying and becoming hot and cold. There's actually I can't remember his name, some guy from A&M that he would do all this stuff looking at the variation in near surface soil temperature, and he was trying to relate that to the microbial activity. And of course it's critical in cotton because there's no freaking residue, so it gets super hot and then super cold and super hot almost daily, I mean, relative,
cycling,
Yeah. But anyway, that's just kind of coming to my mind because we've got this stratification issue that alters our perception of what kind of carbon we can accumulate, like sequestration type issues. It's still highly functional, and we can see benefits from no-till. We just can't measure it because the effect is so shallow sometimes. I mean, some scientists scrape that off and then measure things.
Right, yeah.
But anyway, it's just I hadn't thought about the root exudates stimulating things.
And there's the compounds that leach from the litter above. Those are going to prime the subsoil carbon too, not just...
So that could also explain it.
Definitely. There are people, I think, working on that sort of...
And that would be in contrast...
That would be the fulvic and humics? Or other...
Just like any simple molecule that releases from litter when rain hits it, like what you were saying about nitrogen that's built up and locked up in the litter,
Because even in perennial grass systems, if you scrape off and farm the ground and you put it back in perennial grass, you have this idealistic idea that you're going to accumulate all this organic matter, and you will, but I wonder how stable it is, and then you put like switchgrass and and blue stem and all this stuff. It's deep-rooted stuff, and you wait 50 years. We've got fields that we farmed, and then that's been the condition for the last 60 years. But you look at the accumulation of carbon, and it's not that much. We figure it's too hot.
Yeah.
But anyway, I'm just asking.
Welcome to the halftime show. Man, that was a lot of great information in there. For more information about what the doctors talked about, you can find it, of course, at reddirtagronomy.com. And if you have a question for the group, send an email to podcast@reddirtagronomy.com or send us a tweet. Our handle is reddirtag on the Twitter sphere. And since Dr. Yilling is with us today, we're going to try to get an answer to the question that has been brought up on previous episodes about applying sugar to the soil. You are listening to the Red Dirt Agronomy Podcast. Is it worth putting sugar down as an application? Who wants to take this one?
Not me, Andrea. She mentioned sugar already, so it's up to her.
Well, I didn't realize, that this was maybe something that folks were doing, and I can see the kind of idea behind it, and that you'd prime the microbes, right, and prime nutrient release. But I guess I could see there being some, unintended consequences in the long run, potentially. For instance, what plants are releasing into soil, it's not just sugar. It's like a whole suite of, dozens of different compounds, and that complexity matters. You need to be feeding a whole range of organisms that feed on these substrates or these compounds, selectively. Some prefer this, some prefer that. If you just give all one type of simple, especially something like glucose, that's going to favor the growth of very specific types of microbes that you don't want in the long run to dominate your system, I would say. Also, when you're adding something so simple as sugar, what people are finding is that microbes are decomposing, like using that as an energy source less efficiently. So that means that whenever they use that sugar to then decompose the other organic stuff that's in the soil, they're going to burn off even more carbon as CO2 in the process. So you could, in the long run, have a loss of carbon. Potentially, if you're doing this over and over and over again, you're kind of revving up the release of carbon as CO2 versus, when you have, basically microbes will decompose different types of compounds at varying efficiencies, and you don't want all of your carbon to be released as CO2. You want some of it to be staying in your system and cycling and, remaining sequestered. You need organic matter, right? You need to be at least maintaining it or building it. So, yeah, that's my first answer.
And so you also no, not me first. No, back off. I'm gonna come back. We'll come back. Okay. I have a critical question. Questions first, comments second. Okay. Well, so you mentioned this, and so we're talking about the priming, and these applications on whatever crop might be at planting. So if it's a summer crop, it might be in furrow, it might be in season on wheat, it might be top dress. You kind of mentioned something off the air that I think would be important, is that the plants will signal when they need it, and so this then application made by somebody may not fit that plant's actual need or the soil's need. So can you kind of expand on the plants will release when needed?
This release, this exudation, we call it, this release of the compounds that is happening around the roots we're finding often timed with, periods of high nitrogen demand. So, you want that to be in synchrony, the end release and end demand. So if you're adding sugar at, when did you say that folks are...
So with summer crops, it would probably be pre-plant or in furrow. Some of the stuff I have is applied on the soil ahead of planting, or it would be maybe top dress and wheat, whenever that is, which could be December through March.
Right. So that sugar is going to have an immediate effect. Like you see within hours stuff happening. That's what we see in the lab. And it's a very, very quick spike and a very immediate drop off. So you want that very small window to happen at exactly the right time, and I would guess that a lot of that release is not happening exactly when the plant needs it for growth, or it's a high opportunity for loss, I guess, or a mismatch, you could say.
Well, because kind of what you're saying, and let me see if I get this right, is that it's not long term.
No,
like you're never going to get this
candy.
And it's the exact same thing that we see is whenever we till ground or we burn residue, when we break those long chain carbons, we can explode populations. And if you look at like things like soil health, you're talking about nitrogen, which exchanges. But if you talk about just like soil health, I can make the healthiest looking soil right after I till, if CO2 respiration is your indicator for soil health.
Based on your definition.
Yeah, and so, but what we found is that like within weeks after we've tilled, the population, the total microbial carbon biomass is significantly lower than when we started, because the population crashes because they either run out of sugar, they run out of carbon, they run out of nitrogen, they run out of something, and then your population ends up lower than you had it originally.
Right.
So and kind of like what you said, it's more than just sugar exudates, or that's in that exudates, like signaling proteins and stuff like that are all involved. So it's not just the fact of you get rhizosphere sugar and these exchanges happen. It's dedicated, the plant telling the microbial, the rhizosphere microbes, this is what we need to do right now. And same thing happens when you nodulate, you release the signaling protein and then you start forming the gall. And so like, it's more than just sugar, and sugar is so transient. Like you said, hours, it's come and gone.
Let me just and I'll let you have your comment. Just to clarify, because not clarify, but there's two applications. There's those that believe that are heavily reliant on sugar, and those who are heavily reliant on molasses. Is there a difference between sugar and molasses as far as...
One will be a lot harder on a pump.
Not if you put enough water in it, because this is mixed with water. I just want to get that out there. That there's a heavy belief that it needs to be molasses, and I'm not 100% sure about any.
What about brown sugar? It's got both.
I don't know either.
I don't know. Okay.
I don't know the carbon dynamics of the different sugar compounds.
Me
so
neither.
no.
I don't know if I'm. Yeah. molasses chemistry. Anyone?
Yeah, I don't know. I googled it, and it just says resulting from refining sugarcane.
But
Yeah.
but still yet, compared to like Andrea is saying, is that it says it when it wants it. The likelihood of us being able to exactly time the hours or days that the plant specifically needs it is probably.
I'm also
going to
guess, Andrea, that we spray it once and it's done. The plants are constantly during demand, so it's not like they hit it. It's just this.
Constant release.
Constant
It's not
release.
one pulse. You
Yeah.
know. Yeah, it's a steady release.
All right, sorry. Your question.
Well,
comment,
and
Doc
Josh
Warren.
kind of ruined it for me, but I mean, so
what I
like
do.
when you do it in the lab, right? Do you see what Josh is talking about? If you add glucose or whatever to a soil in the lab, will you see a spike in like the respiration that's much higher than the untreated? And are you measuring the release of CO2 at a magnitude that's much greater than just the sugar being decomposed? I mean, you're seeing.
Yep. Yeah. So we have
Okay.
a way of
I
actually
gotcha.
saying they're decomposing even more than just the sugar. It's like the sugar plus the carbon that's in the soil already.
Yeah.
Yeah, so we use isotopes to do that, which is fun. If we had more time, I'd talk about isotopes. But no, that's what we're looking at is like the sugar. Some microbes might receive that sugar and only decompose that sugar. Like you see a buffet of cookies and you're there for hours and that's all
Well,
you
no, I mean that was what I was gonna say. Is like, yeah, I'm gonna eat the sugar and I'm gonna love it,
Yeah, but
and then I'm gonna
eventually
get all hopped up, and then I'm gonna.
crash. Yeah, but sometimes if it's just the small enough, if it's not too much sugar, that's the thing with these priming studies we do in the lab is you're trying to find that sweet spot, and that's what plants I think are trying to do is that sweet spot of just enough, like the tiniest little sprinkle of sugar. I'm anthropomorphizing too much, but still, just a tiny amount of sugar to just get the microbes barely going, so that they then, are seeking nutrients elsewhere. Otherwise, if you flood the system with sugar, like sometimes we overdo it accidentally with our sugar treatment in the lab, and yeah, there's this huge boom in CO2 respiration and this massive crash, and all they did was eat that sugar and nothing else.
Yeah, but I get fatter when I do it. But
There's that.
you're saying that the soil could actually, which ain't fat is organic matter.
Okay,
Is where I'm going.
that's
okay,
what
You're
it-
saying the soil could actually
Can we get a
lose
flow chart
carbon,
here?
right?
It could in the long run, yeah.
So, but okay, let's check this with environments. Let's say somebody's now in the Corn Belt, and we have really heavy corn residue and high organic matter.
You okay?
Sorry.
He takes objection to this.
I mean, would it be less or better if you're already in an environment that has a ton of residue on the surface and high organic matter? I mean, in our environment, we're kind of already marginal. It's hard for us to make organic matter. We're hotter. I'm just wondering if you would expect if we went to Michigan or
And then added the
Wisconsin,
sugar
and added
in.
the sugar versus our soil environment.
Ooh, it's hard to say. I guess then, yeah, you might have more, various substrates that the microbes can decompose while they're going nuts on the sugar. So maybe there wouldn't be as much of a massive boom and crash. Maybe it'd be
I was
muted
just
somehow. I don't know.
But would
because
it,
I always assume that no matter what we're dealing with in agriculture, that it works somewhere.
yeah, somebody. The thing about it, it's fun. It's easy to poke fun and be critical, but the thing about it is somebody observed this.
Yes, absolutely.
Well, a benefit that they perceived was sufficient to market this product,
But
and so it has happened somewhere.
I think the thing we learn here is that it's scientifically based. That there's
Yeah.
merit to
Well,
it.
yeah,
Yeah.
I mean, she's
It's-
telling us
it's-
what happened. If you want to get rid of organic matter, you can put a little sugar on it.
Well, but I mean, even beyond that, the science behind it is
Yeah.
justified. It's
Yeah.
just maybe misplaced where the science is that the plant releases these same sugars that we would put in
So
through
why
a
would we
plate.
spend our money on it?
Yeah.
But what we're trying to do is accentuate what the plant's already doing, and try to overdo and overproduce. But like you said, just a little bit extra sugar can throw the whole thing into a
Exactly.
whack. And so you're talking about nutrients, and you talk about I don't know if you'd go into a toxicity range, but you put micronutrients at too high a rate and things go
Oh, yeah.
bad. And it sounds like the same thing could happen as if you add in 6 more granules of sugar in in a rhizosphere, it could go really
Right.
You know,
By the way, when we were doing the off time for rates, we were talking the rates about 5 pounds of sugar per acre is the stuff we were telling Andrea about calculating. So the group knows that when she's talking about these rates, it's that 5 pound per acre.
Well, I want to ask a similar question. So there's been work, and I can't remember the outcome of it, but there's work and discussion about like, oh, I've got so much residue. I've got to like break down some of this residue.
Yeah.
And it's kind of one of them deals where I'm like, well, what is too much residue? It's really, too much residue is an amount of residue you can't plant through.
Yeah.
But then there's this interest in people breaking that down sometimes. And one way that they suggest you could do it is by using a flat fan nozzle to put out UAN or something like that. Would sugar do that? Like on the surface, what we're talking about up to now was in the soil, but on the surface residue. Because that's where a lot of people get. I mean, I've never heard anybody say, I'm just tired of all this organic matter. But they will say, I've got too damn much residue to get my planter through.
Yeah. And people are selling a flat fan sugar/molasses over residue to increase breakdown.
Yeah, it does. But what is limiting decomposition in these systems?
Well, a lot of times, to be honest, it's the lack of moisture at the surface.
I was going to say, just add water and there it will go.
Well, and there's
you could add water. But it's hard to get a big enough truck to add that much water. I mean, other irrigation. I'm being facetious, but I think you're absolutely
I don't know.
No.
But it's a lot of in your lower rainfall environments. I was in Ohio last week, and we were in cornfields, and it's kind of cool because like they had all this freeze thaw that had broken up their soil. They almost looked tilled, but they were 25-year-old no-till fields, but they didn't have a lot of residue on them. But then you go out in western Kansas, if they'd had a good crop,
or Dakotas. Or the Dakotas are the exact same way.
Those residues could look like they looked the day it was harvested, depending on how dry it was.
Well, and it's funny that you mentioned that because I was talking with one of the video projects I'm working on. I talked with a producer out in Major County, I believe, and he has been no-till forever, and he said probably this year after this wheat crop he's probably going to have to go through and just do a light till on it. And my brain was like, why? But now I kind of understand maybe why he may have to do that.
Yeah, sometimes there's a perception that they have too much residue. I personally haven't. Yeah, I mean, you get 10-ton biomass from foraged sorghum cover crop or something like that. That's pretty hard to drill through, but through regular crop rotation, you can have some issues with 250 bushel irrigated corn. Irrigated corns it can be an example, but we can usually get through it. Of course, a lot of times in the Panhandle, we don't have to worry about it because all the crap blows in the ditch.
I was about to say it's
well,
but this is the corn on corn is where they come up with this. They're growing 250 to 300
they're wanting
bushel
to kind of
corn
knock down that surface residue so they
although
can
I've seen some Central Oklahoma dryland guys that think they have the same problem, and I'm not 100% on with that board.
100 bushel corn is not going to create this problem, especially if you grow it year after year. Now, if you can somehow grow 100 bushel corn in rotation with 100 bushel wheat, and continuously do that, you might get a little bit too much residue.
There's a lot of interest after last year. We had a really big straw crop last year in a couple of years, and there was some interest in these.
I wonder what would be cheaper if you right now with fertilizer prices. I wonder what kind of cost. Well, of course, I guess we're not going to worry about residue because we're not going to have much, but I wonder what the price point on the sugar deal is.
Well, it depends. So, I mean, some of it's great value and some of it's a high-end stuff. I've been told people just love putting 5 pounds of great value granulated sugar on, and others go with a more specialized glucose product.
You talking
and
about
some
they
go
going
with
to
molasses.
Walmart and getting
a pallet of great value sugar at Walmart,
and the granular sprinkling it that way.
Yeah, just put it in a tank of water and spray it on the ground.
Okay, so it is in a liquid form.
Yep.
That's the question.
They solubilize the in a herbicide application, and I might put it in their nitrogen application.
Well, I learned something.
Hours. Sorry, that's just all I gotta say. Hours is how long it takes for that to be consumed and just totally gone. So
Really?
Yeah, it's. That's why I feel like you'd have to dial it in like real good for it to happen.
Well, now-
at exactly
And then
the
it's
right-
also just it's a shot too. It's
Yeah,
I mean it's
it's
just
just
an
one
instantaneous
pulse.
one shot and
Yeah.
you're done.
Yeah.
Well, then how long could that priming so that's a good damn point. So if I'm looking at this like from a surface residue issue, I'm gonna spray that out there. You're saying if I get good conditions for the activity of microbes, it'll eat that sugar quickly. And then once it consumes that, if it's under the soil, you've got some stable environment for that elevated population to kind of play itself out. But if it's on the surface of the residue,
right, not well buffered, right? It's not.
and not well buffered, I mean, I don't know what the microbial community of a wheat straw
There's a
is.
lot there.
Yeah.
Is there? But how long do you think it would persist after it consumed that
Not
that
long.
sugar?
Yeah, I don't think there'd be kind of a cascading effect necessarily. I don't know if you're getting at that. But
That's what I'm getting at.
Yeah, I think it'd probably be like this, with an hour's boom and bust sort of
So
thing.
I
I could be
shouldn't
wrong.
put sugar on straw to reduce my residue load then.
Well, but once you go back to the whole thing on what's the limiting factor, and even in very wet environments, you still have corn residue that hangs around for a long amount of time, not because of moisture, and it's not because of carbon. It's not unlocking new carbon that's the issue. It's nitrogen.
Nitrogen, yeah, you got that
And-
in and
and
out
I
of
mean,
balance. That's why the UAN has always been.
That is
a-
why
So that
the
would be
UAN is there, and there's
Yeah.
once again there's some science behind it. Is
Yeah.
that you have this 70-1, 60-1
yeah.
residue that you're providing nitrogen,
Yeah.
so it gets closer to that 25-1, so you can break it down. But is it misplaced because you're always going to run into what is that next limitation?
so
does
here-
it turn into phosphorus? Does it turn into moisture?
Here's one of your challenges when you're talking about this residue, and I'd be curious what Andre. But let's say I flat fan my residue, and it rains the next day. How much was of that urea, ammonium, and nitrate was just immediately washed off? And this is something I'd kind of like to look at, because I do wonder when we do our nitrogen timings is if I apply on a straw residue, a flat fan, how long? What's a rain fast? Meaning how long until it washes off? So a small particulate where I'm getting lots of little droplets. And really spreading it out.
Thank you. I
It's
was
a
just-
mist. Yeah, it's
Got
a
it.
mist. And so, I assume if I applied it right now and it rained 4 hours later, all that's going to wash off if I have a good rain. If it's a day later, majority. So I'm kind of curious is how long would it take to not have a washing rain before the majority of that was actually attached to or incorporated into that residue?
I don't know if you would get per se incorporation, but as much as like how fast does that breakdown integration start
microbes.
by the
Yeah.
microbes? Is like, what is that timeline to where it's such a limiting factor that you're starting to break down that carbon so much that is now integrated into microbial bodies and
Yeah.
therefore no longer tied up? Because I think that's the issue we get, is that it gets integrated in those microbial bodies and then is now within a microbial cycle of constantly breaking down. So I mean, how fast would that go? I mean, would that go within, like you said, within hours, or
Maybe. I guess I'm wondering how this is applied, because if it's just a mist, like
It's a mist.
barely moistens things, right?
Yeah, there's not enough moisture. In fact, it's going to be such a high salt content more than
Right.
likely
Yeah.
that you might even have a little bit of antimicrobial within that salt, because I don't know how safe urea ammonium nitrate would be, because it's salts.
Yeah,
I guess I
pretty bad.
imagine there needs to be some critical level of moisture for that to even start to.
I'd assume
get
if you
going,
could do
but-
that in high humidity environment where there's no rain, that'd be a perfect window. But
Yeah, well, and then going back to that same discussion is that sometimes the limiting factor is the bacteria that is going to respond to this aren't the thing that needs to break that down. Sometimes the fungi need to be the one, because it's
Yep.
too long chain of carbon for bacteria to go in and eat those bonds. So now you need the fungi.
Right, we need their oxidative enzymes.
Jason, you were forming a thought, ready to take on the world with a great question.
Well, because do you do a lot? It's mostly nitrogen, mineralization, and dynamics, and carbon. Do you ever? I mean, these plants, when they're looking, like phosphorus and potassium, those are all generally associated with the mineral component of the soil. And, we can talk about, fungi and things like that, mycorrhizal fungi and all that stuff that are interacting. But with going back to this, like, root exudates priming the microbial community, and then, mentioning about how they can, like, direct those microbes to do certain things that they want. Will they utilize that to, like, try to get other nutrients out of the organic matter, or is it mostly just the nitrogen they're looking for?
No, I think there are folks that are showing they do this for phosphorus and other, anything that's potentially locked up in some way in organic matter or associated with minerals, that there are ways that these exudates stimulate the microbes that can solubilize phosphorus, for instance, and release it, or other micronutrients, I'm sure,
like
that are
copper
involved.
Or something.
Yeah,
Isn't copper mostly tied up in organic matter? Isn't that where the copper?
I believe so.
I believe
but
so,
I don't know if
concentrations.
there's too many people think. Look, I just am not familiar with the research on that. But
Molybdenum, I don't know.
Molybdenum.
No.
I had copper questions yesterday, so it's interesting you said
Well,
that.
and that's why I'm asking. You get all these as we go forward and try to increase the performance of some of these crops, and you start picking up, interest in trying to figure out where some of these microbes lie as far as need to apply them and all that stuff, and they're very hard to analyze, I would suspect, especially if the plants are directing the orchestra to try to get them out of organic matter.
That's why in the lab we do a lot of simulate the action of a root, or we have other ways of actually tracing. If you grow a plant, okay, this is getting into isotopes again, but if you grow a plant in a atmosphere where the carbon dioxide is kind of labeled with a tracer, you can then trace that carbon as it's fixed from CO2, it turns into plant carbon. Then you can trace it down into root deposited carbon, exudate carbon, and say kind of how it's priming then how it's released into the soil quantitatively, how it is influencing nitrogen release.
That's awesome. That's bad
but it's
ace
very
right
expensive.
there. That's cool.
When are you going to start doing that?
Once I can get a chamber set up that allows it's very this is not something like on an agronomic applied sense is at all kind of, I think, practical. It's more for like the mechanisms in a greenhouse, grow in a chamber.
But that's in your 5-year plan.
10 year.
10 years.
But this is the kind of stuff, Andrea, that we need here, is because we're living in the field, but we still have to understand the mechanistic concepts of what we do, so we can take. So
yeah, that's
I'm
why I really
loving
I like working with you guys, because some of my stuff is a few steps removed from like the applied and the agronomic work. But I like that you're, I don't know, appreciating it, and we can kind of go back and forth and making those connections. Because I think once like the mechanisms, we solve some things, that it's a few steps before we understand its relevance in the field, and so. I'm happy to be here.
So she's the reason why you take the big freezer out to Goodwill and you do the soil sample, and then you put it in the freezer.
What is my fault?
And then you drive with a
That's
highway
another
patrol
researcher,
escort.
right?
Yeah, it's another researcher. So actually, that is due to her background, but not that. So what we do, we have to haul a big deep freeze with us every time we go sampling for deep soil cores.
And he gets a highway patrol escort from all the way out there. No stopping.
I'd like to know if that's
happen.
my fault.
No, it's not your fault.
Okay.
But so the point is, what we're doing is we're pulling these cores, and the researchers up in Kansas that want the data want the immediate moment of what's going on as far as organic matter, ammonium, and nitrate. If we were to leave those in field moist conditions at room temperature, the microbes are still churning. So we got to freeze it as quick as possible, at least to shut down that process, so we can measure the mineral content of ammonium and nitrate at that moment. Because if we just set and let it just be filled moist for a while, then we might still allow some mineralization, or because we've now induced oxygen, we've introduced a whole lot of characteristics within that 1 meter deep pore.
Wow. So you need like a large vehicle that can store freeze.
Yeah, so we actually bought a chest freezer from Lowe's and have a generator and put it on a trailer.
Oh,
and
wow.
I wish it was colder, but that's about, we can, what?
Well, because buying several hundred pounds of dry ice gets you put on certain lists. That
Why don't you just get a Swan's truck?
Huh?
Why don't you just get a Swan's truck?
I know, at that rate.
Yeah, they even have compartments then.
Hey,
Brian,
if Kansas would give me the money, I'll buy a Swan's truck and drive it out of the Panhandle. But no, so Andrea and I right now are actually working on soil sampling protocols for sorghum trials to understand what delaying nitrogen does to that microbial community, and the fungi community with the crop. So we're really trying to dissect. How do we do this? When it comes to this sampling, when I've done it for other people, we pull a sample, then we have to clean everything with isopropyl alcohol or something. So between samples, it's really important. All latex gloves between samples so we don't have any DNA shifting, those things like that. So it's a whole other world of having 5 undergrads running around with soil probes and 5-gallon buckets you just knock out after the end of each plot.
Josh, you look like you're forming thoughts.
I'm ready to go to anhydrous. I thought we were going to anhydrous.
Well, we can. Do you want to ask about anhydrous?
No, I have no questions about
I have no
anhydrous.
questions either.
You just sounded really excited about anhydrous.
Because we were getting dumb jokes, and Dave has his anhydrous joke.
It's a well-worn anhydrous joke. Well, I shouldn't use the word. My dad actually had an anhydrous. She actually was from Michigan, but she moved to Oklahoma many years after that, and then lived 3 doors down from my grandparents.
Does that make you feel better?
That's the anhydrous joke.
That was a real person?
No,
I didn't think so.
No.
You were almost serious enough to get me to believe you, but
Right.
it had been way too many years. I'm like, the Michigan was a new add-on.
Well, yeah,
that was new.
I had to go back to my actual grandpa. He moved from Michigan. I was like, how can I make this more believable? Yeah, that's how. And then there was another one in there too. I forgot what it was, but it'll come back. So the takeaway for all of the producers that are listening, why is microbial life so important to the plants of Oklahoma? That's a big question.
That is a big question. You're asking me to give the kind of take home there? Yeah, I mean, it's just such a delicate interaction, like this plant microbial interaction that serves to, release nutrients for plants. And it's a hard one to try to, simulate or replace, I guess, by, if we were to add sugar to soils. So I don't know. I feel like there should be a lot of focus on building the, organic matter and supporting many different functions in soil, not just one sort of process or pathway. That sort of reductionist way of, I think, approaching a system is not sustainable, but that's I guess the way I think.
And maybe I want to go ask you this question, Andrea. So beyond building organic matter and those characteristics, what's your opinion about man, the community, thinking that we can manipulate that population within a natural environment?
Right. Microbial husbandry.
Yeah.
People use that.
Mm-hmm. Yeah.
I mean, there's been talk about genetically modifying the microbiome of the freaking soil.
Yeah.
I mean, what do you think about that?
I am waiting on more research, I guess. I'm skeptical. I think there's a lot of kind of not blind optimism, but there's just a lot of how do I say this carefully?
You don't have to.
We don't.
We don't. That's why we do this podcast.
Well, I mean, I think it's worthwhile to do the research.
Yes,
right?
absolutely.
It's I think folks kind of glomming on to an idea and running with it, and then applying those ideas in how they manage systems or what they're adding, what kind of inoculants with this kind of dream and idea that hasn't been verified fully, I guess. There's just still a lot more science to be done.
What's Gail's last name?
Wilson.
Wilson. So this is something she's always said, and it stuck in my head a long, long time ago. NRCS, even pre-NRCS, which was the Resource Conservation Service, or what was it before NRCS, Jason? Soil Conservation Service. Brought in multiflora rose, brought in kudzu, and these were all things that we were brought in for soil conservation, land conservation, and now are invasive species. And so Dr. Gail Wilson once said, when I asked her about the thought about bringing in microbes, she's like, how do you know you're not introducing the next kudzu underground?
Absolutely.
And man, that has lived with me as a very fearful thought.
And you can't see that.
You can't see that.
Well, and Gail's a pretty thoughtful woman. I mean, scientist, she's awesome. Isn't she doing some work, with Carver about, or somebody looking at introducing some of these, mycorrhizal fungi to some of these lines? Maybe not wheat, but something.
think
In sorghum, she did a lot of stuff on
sorghum.
with phosphorus, heavily on phosphorus. So that was
so she she understands and
yeah.
is, like I say, one of these. She's one of these people who's doing research to try to manipulate the biology of plants and soil.
Yeah. I don't know if
but
she's
in a
manipulating the
thoughtful
biology.
way.
So she's looking at species type, especially in underdeveloped countries, to utilize.
Well,
Are there certain species that develop better relationships with those fungi that can then improve phosphorus use efficiency in underfertilized soils? What happens if we were to fertilize this soil and
Maybe
watch
we
that?
should have her on.
Yeah, I think her former postdoc Adam Cobb was working on that.
That is exactly
a lot.
Adam's project.
Yeah, looking at different cultivars or genotypes.
Yep.
Yeah.
But then there's this black box type thought process where you can, like, say I was at a meeting one time, and these individuals in this group, they suggested that it would be better to genetically modify the microbiology of the soil than it was to genetically modify hybrid corn. And I'm like,
It's a little scary.
so how is that any different? Other than I can see the corn.
Right.
And kill the
And
corn.
if I wanted to, if the corn started attacking me, I think I could kill it. But if the microbes, it's just a weird thing to say that it's more acceptable and less risky if you're scared of, genetic modification, but
it's more acceptable to modify the
that's
microbes.
what they said. They're
I
no
would
longer
think-
in business
because
but that's what they said.
the microbes aren't in your food.
Right. No, I get that point, but just thinking about like the interactions and everything that's, the things that are changing day to day, hour to hour, when you talk about microbes, is very different from like a plant rooted in the ground. It's one, it's just different. You
I
can't
can run
compare-
away from that plant.
No, exactly. And I don't know. You could have, for instance, like
It's just a weird thing.
So on that same thought process, is it possible to totally kill the soil? I guess to
that's a
where
good question.
to where there is no more activity under there, and then how is it possible to restart the system? Naturally, not introduce enzymes and such, but is there a way, if it does, air quotes, die, is there a way to bring it back? Am I asking dumb questions here?
No, I mean there are soils that would be deemed like kind of.
It's moderately dumb. Okay. I'm the only master's degree in here amongst PhDs. I'm sorry.
I don't know if I have, the answer, but I mean, there are definitely soils that are unhealthy, right? They're less microbially active, have low carbon, low organic matter. And I guess, my first instinct is always to increase organic matter. That just seems like a simple first step. Because once you support that, you have all these, other adjacent functions that start to ramp up. I actually, have a paper coming out soon that I'm co-author on that's talking about this idea of healthy, unhealthy soils and how you can support, the multifunctionality of soil versus kind of one that's overly reliant on certain inputs. But I think, I don't know what you all think. Like, what would you do to try to recover soil?
Well, the thing that comes to mind when he poses that question is when I was in Virginia, we worked on plasticulture production of tomatoes, and we killed the soil with a product called methyl bromide that's no longer legal to use in the United States.
Gotcha.
Because it would kill everything, and if you got a little whiff of it, it'd kill you too. And
or at least bring some brain cells.
But there was a key thing that you said is that when we did that. Then we gave the reason they did it is to reduce the potential for like disease and pests and things that would be coming out of the soil, and it was cheaper, at least perceived cheaper, to give that plant everything it needed through drip tape fertigation and protect it at all costs, aka kill the soil, than it was to risk an outbreak of a soil-borne disease or insect. That's why they killed it.
But Dave, and I think might answer you had to kill it every year because the microbial population would be able to regain
it would
even after
regain,
that.
and God knows what it would really come back as.
Yeah, 'cause
and
you've
we would
just
usually
completely
rotate, out of. I think they rotate. I don't know what the exact rotation was, but they wouldn't grow tomatoes on the same ground every year. But it is kind of an interesting thing. But like I say, the key point that she said that I caught is that if you do that, you've got to give that soil everything that crop needs.
Mm-hmm. Yeah,
you know what I mean.
Mm-hmm.
And we did.
Well, I guess going back to that thing of can you really actively kill the soil? Like even with that, because you have those
not permanently for sure.
those things that those different organisms that cyst, form these long-term, just if you will, storage structures. We see that with like nematodes that run out of moisture. They they go into a cyst form, and then when moisture returns, they just come out of it. So I mean, realistically, yeah, you can kill the active portion of soil, but I don't know if you could ever kill the soil. Something's going to survive. The like you said though is that what typically will flourish first is you think of soil as an ecosystem. It's those early succession
no different
things
than land.
Fast growing.
And so if you want to think of it from a field that we have massive disturbance on, the weeds are what comes first, and it's those really, really opportunistic bacteria that'll come first, is those other larger species, the fungus, the actinomyces, et cetera, that take years to potentially reestablish. That is what you would do a lot of damage to, but the soil will return. But it's I don't know if you could ever kill it, but you could deem it uninhabitable or unmanageable for a short period of time.
I'm just wondering. I mean, I got some land up by Sayre.
It just keeps going.
It does. It's the joke that never ends. And thank you for listening in on this conversation of the Red Dirt Agronomy Podcast. If you would like to join the conversation, just send us an email, podcast@reddirtagronomy.com, or send us a tweet. Our handle is reddirtag. We would all like to thank Dr. Andrea Yilling from Oklahoma State University for joining us on the podcast today. And to find out more about her or any of the guests, along with any of the resources that we talked about today or any other time on the podcast, visit reddirtagronomy.com. For Dr. Josh Lofton, Dr. Jason Warren, Dr. Brian Arnell, I am Dave Deacon, and we want to thank you for listening. The proceeding is a copyrighted recording of Ag Now Media, LLC, 2022. And yes, all rights are reserved.